Hello YouTube, this is Douglas, and welcome to my 4th Voxel game engine devlog. In this episode, I'm looking forward to sharing a number of techniques that I've developed in order to draw massive voxel volumes on a wide variety of computer hardware. The images currently on screen were recorded in real-time speeds on a laptop with Intel integrated UHD graphics, which, according to GPU Compare, is some of the least powerful stuff out there. Before we begin, I want to briefly discuss the motivation that drove this line of exploration over the past 2 months. In my last devlog, we left off with an impressive voxel ray marcher, written in a Vulkan compute shader. The ray tracer worked well on modern hardware, but became exceedingly slow on lower-end hardware and older cards. I deduced that this was largely due to a memory bottleneck. The ray marcher ran 30% faster on my GTX 1660 Ti in comparison to my 1070, for example, because the 1660 Ti has a third more memory bandwidth. This made me begin to reconsider my approach. As my project developed, I continued to refine my vision for it. I came to realize that, ultimately, what I want to build is a platform, a virtual multiplayer environment in which users can create, destroy, play, and easily extend with mods and plugins. Taking this into account, I decided that my goal should be first and foremost to create an engine that can run on a variety of hardware, including integrated GPUs. Therefore, I pivoted. The first thing I did was choose a new architecture and language for the project. Given my goal of accessibility on a wide range of devices, I thought it would be really cool if my engine could run entirely in a web browser. Native variants would still be offered, of course, but having the full game in browser would make it very easy for new people to try out. However, there was a major problem with this. C# in a browser is slow and not well supported. That's not to mention the existing performance issues that I had experienced with the language. Not wanting to deal with the agony of cross-platform C++ development, I decided to try something new instead. I would learn Rust. It's cross-platform and can be compiled to WebAssembly, which runs at near-native speeds in web browsers. To try and avoid the Rust programming stereotype here, I'll only talk about this briefly. Picking up Rust as a staunch object-oriented paradigm programmer took a fair amount of learning. I had to rethink many of my design principles to take a more data-oriented approach to coding. That said, the transition to Rust has been well worth it. The support for compiling to web browsers using WASM is very well developed. The ecosystem as a whole is just quite fleshed out. The language is more modern than C++, and now that I've learned how to write clean abstractions, I can see the value in features like move semantics. Anyhow, having moved to Rust and the web, I needed a new way to render voxels. The compute shader approach had been a wonderful learning experience, but did not seem feasible on lower-end hardware. No, if I was to draw massive voxel volumes on even integrated GPUs, I would need something different. I would need to take advantage of the limited hardware as much as possible. This would mean drawing triangles with rasterization, which is the one good thing that all GPUs are exceptional at. Thus, I started considering how to draw voxels with rasterization. I had some experience with voxel meshing in the past, having done some small-scale projects with it before. The typical approach, and the way games like Minecraft do things, is to generate a mesh-based hull for the voxel volume. This makes it simple to draw with rasterization. However, this approach has a major drawback. For high voxel counts, it creates a large mesh with many triangles. This is problematic because too many triangles are hard to store in memory and draw every frame. There are some documented techniques to mitigate this. The most prominent is greedy meshing, where adjacent coplanar faces are merged in order to reduce triangles. I like this technique and believe that the greedy meshing algorithms might be particularly amenable to the structure of voxel octrees. However, I was unhappy with greedy meshing because it only reduces triangle counts when faces are coplanar. I wanted to be able to render volumes with detailed surfaces like slopes and still achieve high performance. Ultimately, I didn't want to render a quad for every single voxel face. Considering this, along with my previous ray marching work, I had an idea. I could draw bounding boxes for sections of voxels, and then ray march within them. This would add a little work to the fragment shader, but would drastically reduce the overhead necessary to generate mesh buffers and process vertices. I call the technique that I ended up using Parallax ray marching. It's akin to an existing technique known as parallax bump mapping, which is used for making normals and bumps on surfaces more realistic. You can see it in action on this Wikipedia page. We want to render a detailed, jagged surface without many triangles. Thus, we draw a single, flat quad. Then, each frame, we simply paint the quad in such a way that it looks 3D, changing with relation to perspective. This allows the surface to appear real, but at a fraction of the processing cost. With this idea in hand, I whipped up a quick prototype in C#. The idea was simple. For each 8x8x8 cube of voxels, draw a bounding box. Then, in the fragment shader, perform ray marching inside the box using the same algorithm that I developed for my previous engine iteration, taking the camera's perspective into account. Use this ray marching technique to decide which voxel is visible inside the bounding box. Then, color the surface of the box accordingly. In doing so, the number of triangles I need to deal with is reduced by an order of magnitude or more, while still drawing many voxels. Here's an early prototype of the technique, rendering the Stanford bunny. Here, the bounding boxes are turned on, so you can actually see the surface which is being rendered. Having confirmed that this ran well on my integrated GPU, I set out to optimize it. I implemented the rendering code into my Rust engine and designed an algorithm to generate a mesh haul from a voxel octree. In the process, I applied a key optimization. The algorithm only ever generates tight bounding boxes, such that there is no unnecessary blank or empty space covered by a bounding box. This minimizes the amount of expensive fragment shader invocations, and the amount of ray tracing that the GPU has to do. After a few segfaults, many graphical glitches, and hours of debugging, I finished the rendering code. I added materials back to the game, using some Minecraft textures as placeholders. In addition, I added lighting using standard rasterization-based shadow mapping. Here's the end result. On screen right now are 36 256 cubed voxel volumes. More than 1 million voxels are visible just on the surface of these volumes alone, and my Intel UHD graphics is rendering them, with lighting, at over 60 frames per second. I should mention, of course, that this approach does have its negatives. One major problem I had to overcome was fragment depth. In order to make everything display properly, it's necessary to keep a buffer of the depth of all objects so closer things appear on top. Because the depth of the bounding boxes isn't necessarily the same as that of the voxels, I cannot rely on the GPU to do this automatically. As such, I am forced to manually adjust the depth. At first, this was a big bottleneck, because setting the depth in the fragment shader disables a critical GPU optimization, the early depth test. In the early depth test, the GPU won't even invoke the fragment shader for fragments that are behind previously rendered objects. However, when the fragment shader writes its depth component, the GPU cannot know whether it will be behind something, and so it must always execute the fragment shader. Without early z-testing, my code was very slow. Ultimately, I sidestepped this issue by deferring writing to the depth buffer. When drawing voxel objects, I draw them normally and also render the true depth to a separate custom depth buffer. This allows me to render objects, as long as their bounding boxes don't overlap, with early z-tests on. Then, in a separate pass, I overwrite the depth buffer with the new depth. This works quite well, and I am happy with the performance improvement. One other negative is that this approach prevents MSAA, or multi-sample anti-aliasing, from working. When MSAA is enabled, GPUs blur the edges of triangles, reducing jagged edges on screen. Because I set each pixel by hand, I cannot use MSAA. Instead, I opted to use a different type of anti-aliasing, FXAA, or fast approximate anti-aliasing. This type of anti-aliasing is applied in a post-processing screen space pass and looks quite nice. I think it is a good trade-off for the performance benefits of parallax ray marching. Thank you for joining me to listen about the progress of my voxel engine. I am extremely excited about the possibilities of parallax ray marching and look forward to building out the voxel engine as time goes on. In the next devlog, I plan to add world editing and a fully fledged world loading system for massive voxel worlds. Before we end the video, I'd like to take this moment to briefly thank all of you viewers. When I posted my last devlog, I only had about 80 subscribers. Now I have over 200, we're almost at 250 actually. It's indescribably gratifying to see how many other people are interested in my hobby project. I hope to continue posting updates, more frequent updates now that I'm on summer break, and building a revolutionary voxel engine. Please leave any thoughts or questions down in the comments below. As usual, I'm happy to answer them. Otherwise, until next time.